哎，
看一下这个
嗯哼，
B 是下面多一个 S 是什么意思？
啊，我把它取名字叫 BS，
我是 B
而且其实这个 S 是跟的类似。
那个这个话 PE 光谱提示有跟这种那些这种有主要是一样的非常
因为我放题只是要强调它说里面有题吧，这个就是说它也是里面的一个 vector，就是还是里面一个 vector，它肯定是有题。
什么意思？这个 S
但是这个 signal 的意思吧，可是这个 signal 是什么你不懂，它应该前面有定有 define 嘛？
是的
对，我是说来，它应该有 define 什么叫做 signal 之前，X 应该在前面它会 define，我们没有教的，这个课本题目
嗯，
它应该在那个 section 有解释，是是。哎，
I think there's mistake in the
你
notes.
嗯，
Here, sorry,
这我一样，where is this？这是什么？
internal rate.
8. Is it a tutorial question?
Yes,
Yeah.
I think two.
8. 2 for point what?
Page slide number 29.
I think I cannot find it. Because my version is combined. Lecture 8 has no question 2. You should lecture 8. This one is closing the space. Let me think. Lecture 8 seems like not going. It's coordinate vector.
Yes.
Way to
Textbook.
yeah, but I can't see this question. 32. One.
Yes.
Oh, you mean this guy here? Okay, so everything need to be checked. Yes.
Um,
Which is it? Okay, I'll fix it.
因为它 B 一个是这个是这样，那 B 就等于4，那 B 二就等于-6乘以，那么 B C B B P B Q C 的话就是这个。
对，
那么如果我想求 x
嗯
x C 的话，你就应该这样乘，可是它这样的东西乘不了。
不是啊，这个不是应该长在这里？B C B P B C 在昨天和 B 啊，Hello, morning to everyone. So we will start with where we start in our selection. Basically, this example will include everything we learned before about vector space on span, basis, diagonalization, change of basis, matrix. Okay, so there's a lot of info we can learn from the example that we studied last time. And then after this part, right, then we will switch to a different flavor, okay, to study the geometry about vector space. Okay, so let's start with what we had last time. So we start with a map, a linear transformation. Okay. This linear transformation is given by matrix transformation, in particular this A matrix here. In this case, we will call it A. That's not that's on the transformation part. Okay, so hey, good morning. So the question is, try to find a basis such that you can realize it as a diagonal matrix. Okay. The diagonal matrix we found last time was 5, 0, 0, 3. Okay. How do we find this? Basically, we use the diagonalization method to find this D here. And then we have P here. So let's write down the P. Keywords. Okay, so my suggestion last time was just put your B as your column from your. So this is a suggestion. So we're gonna check what's going on. So, well, first step is, are we allowed to do this? Does the column of P form basis? Why? Why the column of P form a basis? Right? Linearly independent. So why are they linearly independent? Right? Oh, not scalar. Okay, sure, not scalar multiple of each other. But in fact, if you look at a general P, right, it should form a basis of your R and depend the size of your P. Why? Why? Pivot, yeah. So why can you find pivot in every column? Sorry, why the determinant is not equal to 0? Huh? Well, I mean, not all the matrix have determinant 0, right? So why does P have determinant non-zero? Hmm? Correct. Why? Why? Yes, because P is invertible. Right, because P inverse there. P is invertible. Okay, so that's why all these things true. Okay. Right. Okay, so what is going on here? If we let this beta to be this basis here, this means what? If I take any xy from R square here, supposingly I can write it as a linear combination of two vector here. Okay, but not that. What happens if you do this? Okay, what happens if you do this? Well, I mean, if you at the usual way, so if you do the usual way, you can't see the pattern. Okay, if you do the usual way, you will just see that this xy will get sent to 7x plus 2y minus 4x plus y. You cannot see anything useful here. But if you split your vector into this linear combination of bases, then the calculation become very enlightening. Okay, so if you do calculation on here, it is very enlightening. Why? Okay, let me show you in a moment. So if you multiply matrix to this sum, right, you can, because the matrix transformation is linear, right, so you can split the calculation or split calculation like this. Okay, so what can you do here? Are you just trying to multiply like this? You can, but there will be a stupid way to do it. Because why? How did you get this P columns here? What are these columns stand for? Now, when you do diagonalization, what are these columns mean? How do you find them? The keyword is start with E. What are they? The keyword start with E. Huh? Eigenvector, right? They're eigenvector of A. Okay, in particular, the first one is the eigenvector correspond to the eigenvalue 5, right? So you don't need to do the what? The matrix vector multiplication already, because you know that these vectors are the eigenvector. Okay, so they split out the scalar, okay, and then maintain the vector condition. Okay, what's the other eigen? Okay, like this. Okay, okay, okay. So what do you see here? What do you see here? You see, don't you think that the second calculation is easier? Actually, you don't need to do matrix vector calculation here, because you know that this matrix times this vector split out a scalar times the vector. Okay, but in the first case, you need to do a matrix multiplication. Okay, this is a 2 by 2 case, so you might think that this is not far different. You should think about like 100 by 100 matrix case. In that case, it would make a lot of difference here, right? But here, it's still the same. 1,000 by 1,000 also just split out the scalar and the vector. Okay, so we try to capture this idea here. So remember, we have a uh, very convenient tool. Okay, we have a very convenient tool. So what's the tool that? What's the tool here? Is the coordinate vector mapping. Okay, coordinate vector mapping. So still remember, what does this mapping do? So let's say we have this xy here. Where does this xy go? So in other words, what's the coordinate vector of xy? What do you think? What's the coordinate vector of xy? A vector with respect to b. Answer from coordinate vector. What does coordinate vector give you? Start with C, the keyword. Scalar multiplication. Not quite. Scalar, the coefficient. Coefficient of what? Sorry? Ever? Sorry? Yeah, so they give you the coefficient that you need when you want to write your vector in terms of the basis. Okay, so I give you the C1, C2. Okay. But I let you observe something. If we make it into diagonal matrix like this, right? 5, 0, 0, 3. What do you think the eigenvector for this matrix be? What's the eigenvector? Who are the eigenvector? Okay, you can go through your row reduction step, but can you do by induction? Like, say, okay, we guess. Okay, not guess, right? We have a theorem, right? Because this is diagonal triangular. So that means the diagonal term should be the eigen value, right? So now I want you to think about what is the eigenvector for this matrix here. This matrix times what equal to find the original. Huh? Want to guess? Very easy one. Want to guess? What's the eigenvector for 5? Want to try? Hi, Bryson. Want to try? Want to try? 5003 times what vector? Split up 5 times that vector. You want the 5, right? So at least the first word should be non-zero. Sorry? Who's saying something? 1, 0, right? Okay, so let's try. Let's try the 1, 0. Try the 1, 0. Okay. 0. 5003 times 1, 0 is 5 times 1, 0. Correct? Okay. I mean, okay, if you don't like me to jump, I can do this. Okay. Similarly, for 3, eigenvalue 3, you just use 0, 1. Okay. So you can see that what happens, the eigenvector correspond to this matrix error is the two vectors that you found using the diagonalization. But once you diagonalize it, okay, once you diagonalize it, the eigenvector change. But it changed to a easier, how to say, the standard basis actually. Right now, the standard basis. It is always standard. If you look at the diagonal matrix, right? If you're gonna build the eigenvector, it's always standard basis. It's always standard basis. Okay. And then let's say, okay, let's say we pick this span. This R2 is a span of these standard bases. You can see that, okay, what happens here if we set this R2 as basis E1 and E2. Do you know what's this pre-image of 1, 0 here? What's the pre-image here? What's the pre-image here? You know what's the pre-image here? Okay, maybe you need this. So let's say, so C1. So now you take C1 to be 1, C2 to be 0. What's the pre-image here? So if you go back, what's the pre-image here? Okay, so one thing I want you to remember in this chapter here, this square, we call it commutative diagram. This diagram here, how to go back and forth on this coordinate vector, you just remember this. I can express my vector in terms of basis. And then this is the C1 and C2. I mean, the coefficient of these basis vector here in the linear combination. Okay, so this is how you go back and forth. Okay, so now if I fix my C1 to be 1, C2 to be 0, what's the pre-image here? What's the pre-image here? C1 is 1, C2 is 0. Negative 1 and 1, which is the first basis vector here. Okay, so the first basis vector in this R2 here, in terms of standard basis, correspond to the first column in your P actually. Okay, how about the second one? also correspond to the second column in your basis. Cannot. Okay. Okay. So see, you see what happens. Let's show you what happens in this all this diagram here. Okay, so we said that this commute, right? So what does it mean by commute? We want uh, this diagram here. There are two ways. You see, if you follow this diagram, right? I mean the arrow here. There are two ways to start from the top left to the bottom right. Okay, there are two ways, and then we want them to be the same answer. Although we go through two ways, two different ways, but they get to the same answer. Okay, so let's try it. So well, to prove that it's true for all elements, right? We just need to check on the basis element. Okay, so is it better let me think. Okay, let me duplicate them. Okay, so I put it here. Okay, so let's remove these things. Okay, if we want to check on all xy, is enough to look at what happened to the basis element because we can use the linearity. All right, so is it okay? We start with here. Let's start here. Okay, so it's enough to just check on what happened to -1, 1. So, okay, so well, we know that after get sending by A, okay, we know that these are the eigen vector, so they will get sent to 5 times -1 for -1, 1, and then 3 times -1, 2 for -1, 2. Okay, and then how to go forward here? Okay, so this is the first column vector from here from your basis. This will be corresponding to 5 times 1, 0. Okay, this gets sent to 5 times E1, and then the other gets sent to 3 times E2. Okay, so this is one route. Okay, this is one way. Okay, we go one way. How about the other way? Yeah, how about the other way? Similarly, the first column will get sent to E1, right? And then the second column will get sent to E2. Okay, but we note that if we multiply D on these two vector, the first one will get sent to 5E1, the second one will get sent to 3E2. Okay, using this calculation. I don't know. Does it make sense? Can follow first? Can follow? Can follow? No? If not, cannot follow, just ask. Just ask. It's okay, ma. I'm okay, ma. And it's not that I say one time you have to know, because this is not a very usual thing. Any question or not? Yes. 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 Okay, not equal. Send to is not equal. The main thing here is not equal. This is not equal. Not equal. Okay. This map is coming from the coordinate vector mapping. Okay. Not equal. The arrow doesn't mean equal. Okay. Please remember. This is this coordinate mapping here. Okay. So why is it get sent to 1, 0? Okay. Let me show you. Let me show you again. So what's the calculation you need to make here? So you need to ask yourself, who's so find, okay, so like this. Okay, so let me build a question here. Find the vector xy such that the coordinate vector of this b here is 1, 0. Who is it? Who is it? Right. So you need to plug this 1, 0 into your C1 and C2. Correct? Because this is the so okay, so okay, let's write down here. So xy equal to 1 times negative 1, 1 plus C2 times C2 here is 0. So you get minus 1. Okay, so this is the correspondence between minus 1, 1 and 1, 0. Because you see, this notation here very important, this B here. Okay, this is telling you how you express xy in terms of the elements in B. Okay, then you just read out the coefficient. Okay, so this coefficient turned out to be the standard basis vector. Okay, so one thing very important equation you have to remember is this basis. What's the use of basis? Okay, and then the other thing you need to remember is once we express my vector in terms of basis vector, this coefficient are unique or this scalar are unique. But only one way you can get these C1, C2 for 1xy. Okay, so that's why we extract this coefficient out. Does it make sense? No question? Any more question? 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 Yes? No. No, it's not right. It's not. It's not. It's not. It's not. It's not. It is not. Yeah. Yeah. Maybe okay, maybe you are confused with why is this an eigen value, because it's a scalar kind of vector, right? But remember, eigen, what does the eigen value do? Eigenvector do? You need a matrix kind of vector first. Only then you split out a scalar kind of vector. Okay, you need a matrix kind of vector first. Okay, it's not about this right. This right hand side is not very interesting. The interesting part is matrix times vector, then you get a scalar times vector. It's like who is the matrix? Fair enough. On one side, you take a matrix times vector, but on the other side, this matrix disappear, become a scalar. Right, matrix is like n by n size, right? But scalar is just a number. Out of a sudden, the matrix become a scalar. You understand that? Does it make sense? Do you think it's a magic or not? Huh? Matrix become one number only. Okay. Yeah. Okay. Other question? Other question? Yeah, other question? Any other question before I give you some more concept to think about? Any other question? Okay, I can follow this. Make sure you go back when you read it, you know what am I drawing. I hope not become the Egypt wallpaper. Okay, right. So okay, think again what's going on here. So well, we have a matrix transformation from R2 to R2. Okay, but if we change basis, okay, if we change basis to this basis B here, we note that actually what? Actually, our linear transformation, right, act like a diagonal matrix. Okay, act like a diagonal matrix here. Okay, you no need to do this kind of matrix vector multiplication. You just multiply like a uh, multiply like a can you see? Multiply like a uh, diagonal matrix. Okay, and then this diagonal matrix looks clearer if you map this -1, 1, -1, 2 to the standard basis here. Okay, it looks even clearer here. Okay. Can see or not? You see, your matrix A multiply this two vector here is equivalent to this diagonal matrix multiplied on the standard basis. It's the same calculation. Can see or not? Okay, so let me highlight for you what to see here. So can you see that this part of calculation is equivalent to this part of calculation? Can see? Can you see these two similarity part? And observe or not? Try and observe. Okay, so where's the correspondent here? So the correspondent is this part, this part. Yeah, not equal, they are not equal. But what's the relation between them? The coordinate vector mapping. And they are not equal, but the coordinate vector mapping. Okay, so they are equivalent by the coordinate vector mapping. Okay, that makes sense. Question? Go question now. Okay. Okay. So maybe I give you a shorter diagram here. I hope you don't give up. Please don't give up because this is the thing that people already doing. You don't know, then you don't know lah, but people still working in the front. So if you want to work together, just please stop. Please don't give up. Just stop. Just keep working. Okay. Yeah. Because this is a very normal thing that people do already. Okay. It's okay. First time you don't understand. Second time okay. Third time okay. Okay. Just don't give up. Okay. Okay. So let me write down this again. Okay. So let's say you have an eigenvector here. And you apply on an eigenvector. So what happened is um, after going through this P inverse, right, it will send you to some standard basis. Okay. And then after going through this standard basis, this diagonal matrix will easily help you get your uh, matrix vector calculation done. And then it split after going through P again, it will split up lambda x like this. Okay, maybe this one I change color. Okay, maybe I change the arrow color. Okay, okay, so this is what happened when you split your uh, matrix into diagonal matrix using diagonalization. Okay, such that when you do the actual calculation, right? So I mean, in principle, you will just compute ax equal lambda x, right? But after diagonalization, what happens? You take your x, go through this p inverse, you will get the standard basis, and then standard basis multiplied by your diagonal matrix, you will just get the scalar from the right column, and then go through P again, give you back the X. Okay. One question? Question? One question? 有 question？好像4层好像笑了半个钟那边，不知道有什么好笑，人可以跟我们分享一下有什么好笑啊？很有意思，OK，可以，I mean yeah，很有意思啊。如果没有意思，我也不会在这里。Okay, another way to think about it. This P here, right? What does this P do? This P actually is a change of basis from the eigenvector basis to B standard. Okay, so B standard is the standard basis. Okay, let me draw here. And then the eigenbasis is the V1, V2, the linear. And then P inverse, P inverse is the other way around. So from the standard basis to E lambda. Okay, is it correct or not? Let me think. It's the other way around. Because we send the standard basis to, yeah. Okay, so let's think about this first. Wait, did I get this wrong or not? I think this is correct. Standard basis back to, let me think. So let me think how to say about this. Okay, so what happened is we got an xy here. Okay, we write it in terms of the eigenvector. So here is what we call the eigenvector basis. Okay, for every element in xy, we write in terms of eigenvector basis, and then we send it to the standard basis, and then we do d. After we do d, and then we send it back again. Okay, I think this is correct. So wait, let me see what's the statement here. Okay, so the theorem is if you have A that you can write in terms of PD, P inverse here, and then B is the basis that formed by the column of P, then the matrix you can get from the B matrix that you can get from this linear transformation is the diagonal matrix here. Okay, so the picture, let me draw again. So you have Rn to Rn, which is A, and then you can write it as a span of the B here. Then after doing this coordinate vector mapping here, you will transform your A into a diagonal matrix. Okay. Any question? No question? No? Okay, so something you can summarize here is, so if A is diagonalizable, then what is A actually? So A is simply a diagonal matrix after applying a basis change on the vector space. Okay, after you change your basis into your eigenvector, then you just add like a diagonal matrix. Okay, no? Okay. So question before we start a new chapter. You want to ask or you want to test your theory with me? Test your theory with me or not? Okay, so you start with a usual AX, right? And then you go through the X will also go through this multiplication. Since A you can split into this. So you have an X, you express in your, because this X is in the normal Rn, right? And then if you go through this P here, you change basis change, you write in terms of the eigenspace, eigenvector basis. Then you just do the multiplication that I told you last time, right? Okay. So maybe I think I have something useful to write to you. So let's say this eigenspace is V1 up to Vn here. Okay. And then if you put x on this both side of matrix here, what does P inverse x do? So it will first split it into C1, C2, Cn. Okay, but what is this? Where your x, so let's put your x hat here. X can be written as a linear combination of your eigenvector. Cn, Vn. But diagonal matrix multiply this column vector is easy. Why? So let me write down here. Why is this easy? Because if you imagine your diagonal matrix is like lambda 1, lambda 2 up to lambda n, right? What do? You just simply attach the scalar onto the right row. Very easy. Okay, this is the point. Okay, does it make sense? And because you for every diagonal, right, you only really met with one row. Every diagonal only met with one row. You know. Okay. And then you need to send it back to B standard again. Okay, okay, continue. So this will be some level. Any question? No question? Did you guys read my lecture note? You read my lecture note? I think some of you yes, because some of you keep giving me feedback. How about the rest? Did you read? Did you read? No read also can. Just let me know whether you read it or not. Any? Yeah, sure. Yeah. Because in my lecture notes, right, sometimes I will include something that's not in your textbook. Yeah. So if you don't understand textbook, I think you should read my lecture notes. Okay. Yeah. Maybe for this class it's not apparent because usually in my class, right, I will test on something that I say in class. So if you don't understand what I say, I think you will be very pity. But this class is still okay because our questions are quite standard. Otherwise, usually in my class, right, in my personal class, right, I will test on what I say. If you don't understand what I say, you will GG. You know GG? Huh? GG.com. Okay, so make sure you know what I say. Okay, if you don't understand, you should ask me. Okay, because sometimes either I say it wrong or sometimes you think about a wrong concept. So either way, you should really care. Okay, no? No question? Any more question on this part here? Okay, if you understand, try go back and read again, and then try and do tutorial. See can apply or not the theory that I said. Okay, if cannot apply, you let me know again. See where I go wrong. Okay, yeah. Okay, in that case, let's start the new chapter. Let's start a new chapter. Okay, so the new chapter is about orthogonality. So we're gonna explore the geometry of vector, the angle between them, and then their length. Okay, so first thing first, we never define product between vector before. What I meant is, give me a product, give me two products, multiply together, get another product. We didn't do this before, right? I mean, get another vector. Today, what we're going to define is take two vectors, put them together, we get a number. Okay, we get a number here. So let's define it first. This product is a function, okay, that takes two vectors to a number. Like that. Okay, split out a number. So how to split out a number? Well, what you do is you take u dot v is defined to be, you transpose the first one, and then you take the matrix multiplication with the second one. So what happens here? So let's say your u is a n times 1 vector. Okay, v is a n times 1 vector here. What do you do to u? You transpose it such that you get a 1 times n matrix, right? Okay, and then v is still a n times 1 matrix. So altogether, you will get a 1 by 1 number here. What number should we call it? Okay, let's call this one. This guy is a 1 times 1 number. Okay, no? Okay, so let's try. Let's try this. Let me do u dot v first, and then I'll let you do the v dot u quickly. So if I'm gonna do u dot v, what happened is I transpose the first one first, and then do matrix multiplication with the second. And so this is just one row times one column here. Okay, so together we'll get 2 times 3 plus minus 5 times 2 plus minus 1. Okay, so this whole together here is 6 minus 10 plus 4, which is 0. Did I copy something wrong? Yeah. Ah, sorry, this is plus 3. Okay, so we get this one. Okay, so let you try what is v dot u here. Can I compute what is v dot u? This is a very important calculation because this is the only calculation that governs the whole chapter. So this calculation is very important. This dot product here. So this product we call it inner product or a dot product because we put a dot there. One computed the answer. -1. Okay, good. So you transpose your v, okay, and then multiply by u. Okay, so you get 6 minus 10, and then plus 2. Awesome. Okay, so from here, what can you see? Actually, this product commutes. Okay, this product will commute. This product commute because your number commute. So there's a theorem here, u dot v equals to v dot u. And then it is also, so let me put here this commute. We also distribute. So if you take a sum, then multiply, take a dot product with another vector, it's equivalent to taking dot product on both first and then add them together. And then there's a scalar distributivity also. Okay, so the scalar can freely jump between this vector here. And lastly is interesting here. Lastly is about positivity. It's about positivity. So if you take two vectors, dot them together, it's always positive one, greater or equal to 0. You think makes sense or not? Think makes sense? If you have any negative terms inside a vector, what happens? It will get multiplied to itself again, right? So the negative will cancel. Okay, so you add up all the positive stuff or non-negative because you might have 0 itself. Okay, and this is very interesting. If your dot product is 0, there's only one thing could happen. That is, the u has to be 0. Okay, okay, this follows from the positivity. If you have all the positive stuff had to be 0, right? No negative stuff. The only case it could happen is everything is 0. Right? Because you don't have negative number help you. Okay, so it has to be 0. This one is interesting. All right. So out of this dot product here, we will define the norm of a vector. So this is how we define it. So how to find the norm of a vector for the length? We just take. Let me write here. The norm of the vector. We just take it as a square root of the dot product of itself, like that. Make sense or not? Does it make sense? Because v dot v is what? It's v1 square plus dot plus vn square. Why do we take the square root? If you remember the Pythagoras theorem, there's a square root there. Pythagoras theorem. You guys know Pythagoras theorem? Yeah. Okay. So this is the n-dimensional Pythagoras theorem. Yeah. Yeah. So this is coming from the Pythagoras theorem. So if you know it's about a square equals to b square plus c square, right? And then a is b square root of b square plus c square. Okay, well, so I mean, well, what's a, what's b, what's c here? So you should have a picture in your mind here that what is a? A is the hypotenuse side. So this is the vector you should think about. Get the length of this vector here is equals to b squared times c squared. Because if you think about this hypotenuse vector here, it is also equal v equals to v2 plus v3, right? So higher dimensional, why is it true? You want to know or you don't want to know? You guys want to know how to derive it? Okay, maybe I let you see the three-dimensional case. So if we're gonna do the three-dimensional case, let's say we want to figure out what's this length, this V here. But how do you build this V actually? You also need this 90-degree triangle. Okay, so you need to draw the 90-degree triangle first. So how to draw the 90-degree triangle? Potentially it lies here, right? Okay, then the question is how to figure out, let's say, this W and this what this not use Y, the P and Q. Okay, the problem is you need to figure out the P and Q. But Q is easy to figure out, but how about P? Q is just the height, right? But P, okay, P you can figure out using another 90-degree triangle. Okay, maybe call it RS. Okay, so what does it mean? So what does it mean? So can you see here? So V equals to Q plus P, and then P is equals to R plus X here. So what define V actually? What is define V? So this part here, this is okay. So V is equals to V1, V2, V3, right? Okay, so you need to use this three number to get out the length. Okay, so where's V3? V3 is the height. Okay, so let me draw the X, Y, Z first. X, Y, Z like this. Okay, so V3 is on S, Z, and then V1 is on X, and then so here you should get V2 here. Okay, that makes sense. Okay, okay. So the height of this Q should be V3, right? Okay, so let me put here. So, okay. So these are the okay. So okay, this. So let's derive it. Derive slowly. So let the length of Q be V3. Okay, and then length of P to be what? Okay, so how to define this length here? This length here is actually square root of what? B R. See how are we gonna do this? Yeah. So do you know how to find the length of P? I'll rewrite P in terms of R and X, right? How to find the length of P? We need to know what's the length of R and X first. Okay, so what's the length of R and X? What's the length of R and X? Sorry? R is V1, right? About X, V2, good. All right, V1 and V2. Okay, because why? Because R is the length of V in the X direction, and then X is the corresponding to the position of the Y position of your V. You can see or not? Everyone see? Maybe this picture a little bit off, but it's okay. So, what's the length of P here? You use the Pythagoras thing, right? Is equals to what? Square root of 1 square plus V2 square. But you need to figure out what is the length of V. Okay, length of V equals to what? Square root of square root of square root of the length of Q square, right? Plus the length of P square. Okay, so you put them together, you get what? V3 square plus V2 square plus V1 square. Okay. Yeah. So in general, in n-dimensional is also the same. Yeah. So you have a bunch of circles, and no, triangle. Okay. So why Pythagoras theorem is very useful because we can generalize this right angle triangle way to calculate things. Okay. You know what's the story about this Pythagoras theorem? You know why Pythagoras think about this? You know where Pythagoras live? Where Pythagoras live? He's from Egypt. You know Egypt? 金字塔 pyramid. You know pyramid? They measure these what do you call it? Triangular prism. What's the name? Long time didn't mention the name. What's the shape? Pyramid shape? This pyramid shape, I think there's a mathematical term, but I cannot recall now. So that this pyramid shape, right? There's a 4 corner, right? Those corners should be right angle, right? Okay. Another thing is in that area, they need to like divide lands to people. People need land, right? So they okay, they are not farming because they have a river, right? What's the river name? Anyone know? Nile, right? Okay, the Nile River is very great. So people just live around there. Okay, so what they do, I think, is catch fish, maybe. Okay, so they divide lands for them to live. Okay, so they need to measure the land. Right, they need to measure, this square or this rectangle is for you. Okay, if you measure wrong, what does it mean? If your square, if you're going to give a square, but if you start measuring, you have a little bit off. Means what? You might sometimes either give more land to a certain people, or sometimes you give less land to some people. So it's not fair. Okay, so to make sure that they do a right angle length, maybe they can use this Pythagoras way to check whether they have the right angle. Okay, because in old days, right, they don't have this fancy apparatus like what we do now. You guys know how they measure the road? Make sure their road is straight or something like that. You know? Have you ever seen the people taking a machine standing on the road, a stand with a stand, then uh, look through the lens, right? But in old days, how do they check? Okay, if it is the right angle, it should satisfy that a square equals to b square plus c square. Because what they have is just ruler. You just pull a ruler across 2 points. That's all. You understand? No? Okay, so to make sure that they really draw a right angle, you just check whether this length of this two endpoints here satisfy a square equals b square. Okay, yeah. So people say learn maths are useless because they come from a real life. Okay, we already abstract the idea. Okay, actually, why we think about maths is very practical. Yeah, they want to like divide lands fairly. Correct. Okay, otherwise, do you want to get this land or this land? Huh? Which one you want? I give you pick. This one, right? You have to get more, right? But if one of you get more, the others should get less already. So to make sure equal, we have to draw the right angle. Yeah. Yeah. Okay. Right. So let's see. Next. So the conclusion here is how we define the length is the square root of the dot product with itself. Okay, with itself. you dot with yourself, you can get your length. Okay, you dot with yourself, you can get your length. Okay, let's quickly do this example. Show that if you compute a scalar multiple of v, you can just simply pull out the scalar. But the scalar here, there's no minus sign anymore. Okay, you make it absolute value. So let's see what happens here. So quickly do it. So if you're going to compute this, what's this definition here? How to compute length of a vector? You dot with yourself. Okay, so you that CV dot CV and then take square root. Okay, but what's the property of dot product? You can pull the scalar anywhere. Okay, so pull it out. Okay, but you got the square root on c square, right? Meaning what? It's just the absolute value of c. Okay, so it's just the absolute value of c times the length of v. Okay, so meaning this c square will clean your minus signs here. Why this magnitude makes sense? Why does it make sense? Because you won't get negative from the square root. Square root function won't give you negative number. Right? Okay. Square root number won't give you negative. So one thing maybe I need to let you know is if you have a square root function, right, it only live in the positive part or non-negative. So the picture of the square root function is like this. And also you cannot put negative number, otherwise you go to complex number. Okay. So square root function only defined for the positive. Okay. Yeah. Anyone told you before? Did you learn this before? No, got. Some of you got, some of you don't have. Okay, but make sure you learn it today. Okay. Uh, yeah, let's see. Okay, let's do one more and then we'll take a break. So let's do one more. So let V be this vector, you see? You see this two notation is what I told you before, right? Okay, one is in a point form, one is in a column vector form. Okay, these are the two same thing. Find a unique vector in the direction of V. Okay, so here, there's one term I want you to learn here. There's one term I want you to learn here because this is pretty important later. So this is called unique vector. Okay, so let's draw out this V here. Oh shit, this V is a four-dimensional guy. Okay, so let's draw an abstract vector like that. So this is V. Okay. In principle, this V can have any length. Okay, can have any length. Only zero vector have length zero, okay or not? This one, every one of you agree, right? This is what we discussed just now. V dot V equals 0 if and only if V is 0. Okay. So if you have a non-zero V, it should be non-zero length. Okay. And then what does it mean by unique vector in the direction of V? Meaning I want the same direction, but so let me put here. I want the same direction, but the length is 1. Okay, so what we do is we take the V divided by its length, Does this make sense or not? Do you think this makes sense? No. Let me prove to you. So what I want to prove to you is the length of this new guy here, right, should be 1. Okay, should be 1. Okay. Okay, so let's prove this. Maybe let's prove this before we compute. If you're gonna do this, what do you get? So you need to ask yourself, what is V divided by length V dot V divided by length? What's this? Hey, this is just a number. Don't look at so many lines, you will go crazy. These two are just scalar number. Okay, just scalar. Treat it as C. C like that. So what happened? You can pull it out, right? Just pull the C out from the dot product. and then you have v dot v. But what is v dot v? What is v dot v? Huh? The length, right? But do you think it's a length square or just length? Length square, right? So the length square cancel out, you just get 1. Okay or not? Okay, so this is how you find the unit vector. So in this case here, what do? We need to compute what is the length of so the length of v equals to what? Square root of v dot v. So in this case here, can we quickly compute it? Let's move this. So can we compute this? So 1 dot 1 plus minus 2 dot minus 2 plus 2 dot 2 plus 0. So we get 4, 5, 9. So square root 9 is 3. Okay. So the unit length here is v over this length. So you divide the vector by 3. So this is your unit length. Okay. Any question? Okay. So for this part here, I want you to appreciate the inner product and this unit vector, because later on we were going to play around with these two things. Okay, how to get a unit vector and then how to take dot product. Very important. And the length function. Okay, let's take a break until 10:18.
我想问就是那个 eigenvalue 跟 eigenvector
这样
就是 eigenvalue 嘛，
没有错
这个等于 eigenvalue 乘 eigenvector 是，
对，没有错。
所以我们其实这个 equation 是等于我们的 eigenvalue 乘 eigenvector 是一样意思的，那个
是没有是等于吗？对，等于对
这个是 eigenvector 来的，
对，没有错，
像这个
也是啊，就是它自己啊，两个是 x 嘛，
都是它的 vector 来的，
谁的 vector？
这个 eigenvalue 的 vector，这个也是 eigenvalue 的 vector，还是它本身的 vector？
你讲的这两个都是
因为eigenvalue 的 vector 是找来这个是比如什么东西啊，
OK，好
说做
OK，对，OK，好，对，没有错，
所以这个是
对，没有错，没有错。
其实什么是 diagonalizable？
diagonalizable 哈，
我们懂啊，我们在找第一个 P 啊，那其实它什么意思
？OK，找完 D 跟 P 过后，它这个会符合这个条件，会符合这个条件。一开始你不知道这个条件在干嘛，但是它就是符合这个条件，它就是符合这个条件罢了。diagonalizable 的定义是这个，比如说 A similar to 一个 D， 就写在这个条件。
A P 的 A 的 P 对
吧？OK，sure，因为这个两个是 equivalent，因为 invertible 嘛，你可以乘两边 P， 或者乘两边 P plus。
但是 P 不是等于 I 的，
怎么？
因为正常 I 等于 A 减1嘛。
喂，没有啊，不可能啊，不可能啊，因为 A 不一定等于 A 减1。
因为我们做 three matrix 过后，
哦，不一样。OK，你要记得啊，这个东西，这个是一个 augmented matrix，有差别的。这个两个放在一起啊，我没有乘在一起，我只是在做 row reduction 罢了。但是这一个哦，是真的把它乘在一起。这个我没有跟它乘在一起，这个我只是在做 row reduction 吧。他们两个没有被结合在一起，这个东西是被结合在一起的。这个 AI 其实是 A 来，对吗？identity 乘所有的 matrix 都是他自己嘛。对，OK，不要跟这个混乱，因为虽然我们都是放在隔壁罢了，但是一个是可以合在一起，一个是不能合在一起。哪个？
这其实是
合在一起。
我懂了，这是其实 diagonalizable 的 matrix 啊是 A 来的还是 D 跟 P？
A，我们是指 A，如果 A 是 diagonalizable that exists 这两个东西 such that 这个是 true。
那就说
A
还是
is 这
true
个
啊。
，then that exists 这个 such that 这个是 A 本
A
身
是哪一个 variable if
if
有 P 跟 D 啊？
对 such that 这个对，
对的，就把这三个乘起来啊，我要找个答案。
然后什么答案？
如果要 prove 这个东西是对的，就是 prove D 跟 P 存在吧。
对对对，存在然后符合这个条件，两件事情，一件事情，两件事情。
这个呢就有意思。
啊，就是这个意思哦，就是这个意思，把它写成这个状
哎，这
态，
是这是数字的意思哦，但是它本身有意思哦。
本身有意思哦。我在想想你这句话什么意思？
这是用 P 跟 D
对，做出来的哈
用 reliable 来做
啊
出来，但
，OK
是
OK，好好
但是
好好
它没有意思的话，两组可以用。
，OK OK OK，好，可以，OK，好好好，OK OK，意思就是我刚才讲的那个意思，就是 change of basis 的意思，其实 change of basis 的意思就是说你本来是说可能你这个 v1 嘛给 send 出 lambda a b，不对，
嗯
但是哦，我可以把它简化版，我可以把它看在这个有 d 这个 d 上面有 lambda 一的身上，然后这个的 eigenvalue 很简单，eigenvector sorry，它就是 standard basis 吧，sorry，但是怎么 go through 这边呢？就是用刚才我们讲的那个呃
，coordinate
connect vector。OK，现在我用 e lambda，因为我把它想成是 span of 它的 eigenvector。他的意思就是 change of basis，就是说啊，我不要做这个东西，我不要直接拿我的 x 去乘我的
啊，
eigenvector，instead 我把我的 eigenvector 送去它的 coordinate basis，就是1000，然后1000被这个作用过后，就直接调出 lambda 10000，然后再把它送回去它的那个 eigenvector，你知道有什么差别吗？在这边？
比较方便一点的。
对，没有错，
但所以它的，
我先送过来，我送过去，再送回来。
所以它最后的层次讲，
什么？就哪一个
就是它最后
哪一个
的两个
哪一个组？
vector 是什么 vector 乘什么 vector，
在哪里？在哪里？
就是这个到这里嘛，这样
对，
嘛。
没有错。
它最后的其实它的那个 matrix 是这样，两
谁的 matrix？
就是因为你做完
你写。
这个步骤嘛，
对，
它一定会变成什么东西，成什么东西啊？
这一个变这个
这个变这个，这个变这个，这个
，OK，然后
是等于 scalar 乘什么东西？这边还
喂
是哪个呢？乘什么东西？
喂，你想想你的什么意思？你这个是什么意思？
哦，这个东西到这里
嗯哼，
就是这个东西来的。
对对，这东西对，I mean，OK，这一个是走下面这条路，
OK，
这一个是走上面这条路，所以两条路是一样的，等于对吧？
嗯，
嗯，你这个是什么意思哦？不懂的这个什么意思？
因为
嗯，
这个是等于 D 还是 P 哎？如果是这个到这里
哪一个？
走一条路，
这个就是下来就是 P inverse 哦。哎，喂，sorry，不可以这样子跟你讲，可以这样跟你讲吗？
上面去 P 嘛，上面去 P 那个什么？现在
是吗？是这样想吗？我想一下。
对，上次上面就是 P 嘛，下去就 P 那个什么？
OK，好，OK，可以，OK，OK，
D 是这里，
OK，好，可以，可以。我再想一下，他是不是真正在做这件事情？上去是不是 P？啊、上去是 P，是，这样，这样
那就是你 P inverse 的意思，就是这个 P 的 inverse 的意思吧？
对，真的就是那个 P inverse 的意思，真的，yeah，
具体解释。
因为哦，你看你拿你的 P 啊，乘你的第一个东西，是不是会调出你的第一个 P 那个？它就真的掉出来，它真的还回你的伊兰达里面的东西，一个一个还给你。 对吧？因为我们讲 build 这个 P 就是把 V1 V2放在这边，所以 standard basic 就一个一个给它读出来，
嗯，
明白？
就是1001就是 V2的一个
啊，对啊，对啊，对啊，对啊，因为 exactly 啊，因为就是我们刚才讲了嘛，因为 CV1、CV2加 CV3嘛，加到加到 CN 对不对？所以我们让水复活水哪个 VN 对
嗯，对，
活着
对，这个步骤是哪个 P 呢
哪个？
？P 的步骤啊，这个找出来那个 V
对
上去这里，
对对，你先把 V 的东西放回这边，因为我要让那个 diagonal 容易算嘛，
嗯，
算了过后把它还回去，这个是这边的这条路啊。
对
来，
老师，
来，
我感觉上节课的时候理解跟这节课感觉，
你说说看。
因为
嗯
我是觉得这边的空间是当成是那个机向量的那个，然后这个是由那个碳特征向量，
嗯，
对，然后我的理解是像这样子变过来，就是类似于这样变，这个是这样变，也是另一个理解方式。然后我看到他讲的是
对对对
A 的是你说这个空间是由 A 的特征下反过来，
，OK，好，
这应该理解的可以。
不能，其实上次我讲错，所以我卡住。
所以
上个礼拜啊，不行，因为上个礼拜就是因为我写错了，我觉得我有两个地方写错，所以我一直卡住。上个礼拜，
这个为什么？
对，不然下一个 break 我再跟你解释。下一个 break 可以吗？我们开始先，OK，我下一个 break，下一个 break 啊，我们先开始的，啊，快上也可以，也可以。Okay. Maybe you are concerned with last week that I explained about that, not last week, last lecture, the one that I drew in the class, right? So that one is wrong, because that's why I get stuck, because I draw wrong stuff. Okay, that's why I get stuck. So please use the explanation that I gave today. Okay? And the one I provide in the notes. That's why I get stuck last lecture, because I put wrong space. Okay, next. So, hey, okay, next. Well, so how you gonna explain? How do you compute the distance between U and V? So what's this idea here? So you got U, right? You got V. How do you measure the distance between these two things? Oh, what do you think? What do you think? How to measure the distance between these two? Where do you put your ruler? Where? So you pull from one end to the other end, right? Where do you pull? I don't think you will do this, right? Not this also, right? Okay. So we put uh, the ruler at the end of both vector here. Then we're going to compute what's the length of this vector. Let's call it W. Okay. So do you know what's the relation between W, U, and V or not? U plus V W. Huh? So you need to follow the direction, right? Okay. So what's your direction? Where's your direction? V W equals to U. Okay. So how to check this? You need to check the starting point of your vector and the ending point of your vector. Okay. So if your U start, let's say call it A, and then B end at U end at B, then
What's the other sum? You also start from A, but maybe you bypass C first, okay, and then go back to B. Okay, so you have U equals to V plus W. But now you're gonna find the length, right? So the length of foo actually is the length of W. So actually you need to find what is W first. W is equals to U minus V. So that's why the length of W is the distance between U and V. Okay, no? But also makes sense, right? U minus V. What's the difference between two numbers? Also take the difference. Okay, so it's similar to number addition. Wait, when I ask someone call me, let me see. Hello? Yeah, hello. Okay, okay, okay. Kalau pakai apps boleh. Okay. Boleh. Tapi tak boleh buat melalui app lah, sebab sekarang kita ada lah itu. Okay. Jadi kamu cakap campaign untuk 18 itu. Okay, 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 okay. Okay, yeah, understand. Okay, yeah, okay, 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 okay. Thank you. Okay, thank you. Bye. Okay, hello, testing. Okay, continue. So the length, the distance between two vector is just you take the difference between two vector and then you compute the length. Okay, very straightforward. Okay, straightforward. Okay, and then it's a Cauchy-Schwarz inequality here. What does this Cauchy-Schwarz inequality says? If you take the dot product between two vector, okay, because potentially you might get, would you get? Yeah, you will get negative. Okay, so if you consider the absolute value of it, it is always less than or equal to the length of U and V itself. Okay, so this is the Cauchy-Schwarz inequality. I think we won't prove it. We won't prove it. If got, I just provide you the proof. Okay, but the idea here is you take the dot product between two vector. Actually, it's less than or equal to product of their length. Okay. And in maths, you always see this kind of property is when we combine them, we want to compare before combining them. Or not. Okay, you see, u dot v already combined them. Okay, but we want to see what happens if we just split them off. Okay, we want to compare these two quantities here. Always we want to do this. Linearity also like this, right? We send the sum is equivalent to sending the sum of sending separate vector. Okay, so we're going to compare. Okay, what we do to them afterwards and before. Okay, we always want to do this for mathematics. Okay. Next, it's about angle here. So the angle here, maybe this is not very enlightening. So one thing I want you to see is u dot v is actually equals to the length of u times length of v times cos theta. Okay, so that's why they get this theta formula here. Okay, so if you take u dot product with v is what? Is a number, right? Okay, so what this number means, very important. Because you know that if u dot u is just a length. What happens if you take different vectors together? It's another number, but what number is that? Oh, actually, there's a relation between the length of u and length of v and their angle together. Three pieces of information put together. Okay, length of u, length of v, time, the cos of the angle. Okay, three pieces of information live inside this dot product. Okay. Okay. Maybe you were interested why is this true? Actually, this can be proven from the law of cosine, if you know. Law of cosine is the c squared equals to a squared plus b squared minus ab cos theta. It's a variant of the. Let me put here. Oh, this is proven. Law of cosine. Okay, so this is the variant of Pythagoras theorem where you don't have a right angle triangle. Okay, so the angle here is theta here. So this is the law of cosine. You can prove it from here. Okay, for this one, I will provide you. No need to worry. I will provide you. Okay. And then two vectors are orthogonal if and only if u dot v is 0. Okay, because when is cos theta equals 0? So what's the cos function here? So when is it 0? It is when it is 90 and 70. Maybe in max, we will prefer to write it as pi over 2 and then 3 pi over 2. So we'll say that two vectors are orthogonal if and only if u dot v equals to 0. Okay, why is it true? This is coming from this angle formula here. Okay, so far okay? No question? No? Okay, straightforward then. Okay, so right. Okay. I think should we prove these? Not very important, I think. Don't need to prove this. This is not very important. If you want, you can try if I set as homework. Not very important. Not very important. Left as homework if you want. I think I will provide also the solution. Okay, let's continue. Okay, let's learn about this. Orthogonal complement. So let W be a subspace of Rn. So by now you should be very familiar with the subspace right here. So subspace is the space that satisfies three property. There's a zero vector, and it's closed under addition, closed under scalar multiplication. Okay, and then we're going to define another space called an orthogonal complement. Okay, orthogonal complement. So orthogonal means 90-degree, right? Complement something else. Okay, something else. Complement. So complement to what? So it's the orthogonal complement of this W, this subspace here. So how to figure out what is this orthogonal complement here? We put it as a W perp. Okay, so this is called a W perp. Okay, is equals to all the vectors such that the dot product with W is 0 for all the vector inside of subspace. Okay, and then we will show that this is a subspace. Okay, so this is a subspace. Okay, do you know how to do this is a subspace? What to do as an exercise here? Let's do as an exercise now, how to check this is a subspace. Proof. So the first question is, obviously, I mean, the zero thing you need to check, the zero condition you need to check is this set should be a subset of Rn, which is very obvious. Okay, so then the first thing to check is whether 0 is in W perp or not. Okay, meaning what do you need to check here? You need to check that it satisfies the set condition here. Okay, so you need to ask yourself, is 0 dot with everything equal to 0 or not for all W in W? Is it? Yes, right. Because what? Because what you get is 0 times W1. Okay, let's say we write W equals to W1, W2, up to Wn. What's the dot product? It's just 0 times W1 plus 0 times W2, and then so on. So you can get 0. It's a sum of 0. How about second? Okay, if V, let's say if so left X, let's say X and Y are both in W perp. So the question is, what happened to X plus Y? X plus Y times W, what do you get? Just now we said that it distribute, right? So you get X dot W plus Y dot W. But both of them is in W perp, meaning what? These two quantities should be what? If X in W perp, Y in W perp, meaning X dot W and Y dot W are all over. What do you mean? Huh? Hello? Hey, there are 90% here. Zero sum. What do you get? 0, right? Okay, 0 plus 0, which is 0. Okay, for all W. So this implies that, this implies what? X plus Y is also live in W perp. Okay, similarly, you should do it for scalar, right? So you could, can you imagine what's the calculation for scalar? Maybe we just write it quickly here. What's the calculation here? You just do Cx times W. Okay, such that you get C times 0, you also get 0. Okay, so write all the steps down. Okay, does it make sense? Okay, you can fill it in yourself. Okay, next. So this theorem maybe not very important for exam, but just for some facts. Let A be an n by n matrix. The orthogonal complement of a row space is actually a null space of A. Okay, and then the orthogonal complement of the column space is the null space of AT. Makes sense or not? Makes sense. Makes sense. Ever say makes sense. How do you think about it? Maybe just talk about the first one. Let's talk about first one. First one is more obvious. So if you put A right as a like n by n matrix here, what's your null space? Is the thing that you multiply to the right hand side. Okay, but when you do this multiplication, right, what do you do? Row times columns, right? Then this is the dot product between the row vector and the column vector. And then the dot product of these two you get what? 0 everywhere. Okay, yeah. So this is another language to talk about null space. It's an orthogonal complement of a row. Okay, and then here, when you talk about orthogonal complement of a column space, try to write it down. Actually, you need to talk about null space of the transpose. Okay, I suggest you to write it down. You cannot just read like this. Okay, you need to write it down. What does it mean by orthogonal complement of a column space? Okay, something that you dot product with all the column here. Okay, so if you turn your, if you flip your A, right, then it will be like doing the dot product here again. So you try to flip your A. Okay. Okay. Yeah. Okay. First thing is the first one you need to appreciate because this is what you have been doing already. This is the calculation you have been doing. Okay. But the second one is orthogonal complement of the column space here. Okay. So meaning you need to have a vector dot with all these columns. Okay. Get 0. Okay. So if you go, yeah. Okay. So this is the hint I gave you for the second line. But I think we won't test it for this theorem here. Yeah. Okay, this is another language to talk about null space of A. Okay, any question on this part? This first line should be very familiar to you because you are keep doing this calculation for 4 weeks already. Okay, but the second one, I suggest you to write it out and then you will see it. It's not far from the first construction here. Okay, after you flip your A, it's exactly the same calculation. This is the hint I gave you. Okay, yeah. Okay, right, continue. Next. Next is about orthogonal set. Okay, orthogonal set. So what's orthogonal set here? A set of vector is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. So what does it say? So if you want to say that a set, let me highlight. If you want to say that a set is orthogonal, you need to check for each pair. Okay, you need to compare every pair. Okay, whether it's orthogonal. Okay, let's do it. So examples here. Show that these 3 vectors is an orthogonal set. So how many dot product you need to check here? How many? How many? 3. Okay. You need to check 3 dot product here. So you need to check U1 dot U2, U1 dot U3, U what? U2 dot U. Okay, so you need to check 3 of them. Okay, try check. Okay, try check. See if you get 0 or not. Hey, by the way, for those who haven't seen your quiz, right, you can message me. We'll take a photo for you, or maybe I bring it on next Wednesday. So I think we will try to discuss quiz on every Wednesday, right? So next Wednesday we will discuss quiz also, and because next week is the next final week, right? Maybe we'll take a post class photo before we finish the semester. Maybe we'll do it on Wednesday also. Yeah, maybe Wednesday I don't help my other class. They are free. Today they are not free. So maybe we take photo on that day. and then we'll see how our syllabus go, and then we'll decide what's the last 2 days we're gonna do. Okay. Yeah. Okay. Did you guys see 0 on all cases? For first cases, you get -3 plus 2 plus 1, so get 0. 3 plus 2 plus 1. And the second case is the same, right? Wait, why is it the same? So this is -12, -2, and 7. So it is 3 over 2 minus 2 plus 7 over 2. Alright. So do you get 0? 4 plus 3, 7. So I get 0. Plus 1, you get 1 over 2 minus 4 plus 7 over 2. So what do you get? You also get 0. -7 over 2 plus 7 over 2. Okay. So since all pairs, each distinct pair is dot product to 0, right? So since each of them dot product to 0, then this set is a orthogonal set. 0 form. All right. How about the next one? Linearly independent. How to check that? What do you do? Maybe you tell me. We're not calculating this. What do you do? What can you do? There are a few ways to do it actually. What can you do? And maybe different people give different answer. What can you do? Amber? Huh? Augmented matrix? Sure. So you put them together, right, as a matrix, and then you solve it. Not solving it, but you row reduce it. Okay, so if you row reduce, you should get something like this. Any other way to check or not? I see if got other people learn from textbook or what. Something that I didn't stress on in class. So so why you can deduce? So if you row reduce such that every column, okay, has a pivot, it will imply that the column vector will form a linearly independent set. I said that there's another solution. You can solve it the other way. What do you think? Maybe it's helpful for this week quiz. Yes, good, very good. So what do you do? What do you expect here? So let's call this A. You should expect that the determinant of A is not 0. Okay, if it's not 0, that means this is a square matrix, right? So it should be invertible. So A is invertible. If you want to link back to the first answer, right? If it is invertible, A is row equivalent to identity. Okay. Okay. Any other answer you can give? Any other answer? Not on top of my head. Do you have? I think this is the 2 I remember. Oh, there's one more. I mean, it's solved from the original definition, but still you need to do the similar calculation part. Yeah. The C1V1, C1U1 plus C2U2 plus C3U3 equals 0 if and only if C1, C2, C3 equals 0. Yeah. But if you're gonna check that solution, it's also equivalent to solve the part A or reduce the part. Yeah. Okay. Good. All right. Next, theorem. So if X is an orthogonal set of non-zero vector, then X is a linearly independent set. Okay, so this is a new way to check whether a set is linearly independent or not. You just check that whether it's an orthogonal set or not. Okay, just now I asked you to check orthogonal set, right? And then you see that actually they are linearly independent. In fact, it is always true. Okay, it's always true, and hence is a basis for the subspace that's spanned by X. Okay, so this is very matched up with your intuition for the standard basis in R2, or the x-axis, y-axis, x-y-z axis, they are 90 degrees to each other. And then they are linearly independent of each other. Okay. So this is the third way to do the checking. You just need to check that the set is orthogonal. Okay, then it will be linearly independent. Okay, so this is a very cheap way, okay, to check whether the vector are linearly independent of each other. Because you should know how many ways you can draw linearly independent vector here between two vectors. Actually, there's really only two ways. I mean, not two ways, but one cases is 90 degrees with each other. The other cases is not 90 degrees with each other. You go ahead. Linearly independent. Okay. Does it make sense? Remember, for two-dimensional case, right? I mean, two-vector case, if they are linearly dependent of each other, they must be scalar multiple of each other. They must lie on the same line. Okay? If they don't lie on the same line, there are few cases. Either they are 90 degrees each other, either they are not. If they are 90 degrees each other, they must be linearly independent. Okay? So this is the third way you can check. No need to do row reduction one. You just do dot product. Okay, so to check linearly independent, you can do determinant, you can do row reduction, you can do dot product. Okay, but this one a bit risky. Why risky? If it's not orthogonal, it doesn't mean they are not linearly independent, because it could be the other case. A bit risky, unless you use your inspection, see roughly all zero, then use dot product. Otherwise, this is only one direction. So let me write them here. Orthogonality implies linearly independent, but not the other direction. Not the other direction. Okay, because you can have the other picture here. Okay, which are also not linearly independent, but they are not orthogonal. They are linearly independent, but they are not orthogonal. Okay. Yeah, so only one direction. Okay. Next, an orthogonal basis for subspace is a basis such that it is an orthogonal set. So this is what we define as an orthogonal basis. So you have basis, and then you check their dot product. Okay, between two vectors, it is always zero. So we call it orthogonal basis. Very intuitive. All right. Next. Then what do we do with this orthogonal basis here? This is very special now. So for each y inside the subspace spanned by this orthogonal basis, we have a way to find C1, C2, up to CP. We are not using row reduction anymore. We use dot product also. Okay, we are using dot product also. So how this dot product comes out? So how to figure out the coefficient here? You take your y, okay, you take your y, go and dot with every basis. Go to dot at every basis, divided by the length of that basis. Okay, this is your scale. Okay, so this is your scale. Okay. And this is your scalar. Here. Okay. Let's see if I have this proof or not. Okay. Up here. Let me put it back. Okay. Why not? Like this. Okay. Okay. Yeah. You want to know why? You want to know why? Okay, let's compute first. Let's compute first. Let you see what is going on here. Then maybe we'll see if we want to know what happened. Okay, so like you see this question here. This question is like a 2 weeks ago question. Okay, you have U1, U2, U3, and then you want to spell it as a linear combination. Meaning what? Does the y live in the span of these three vectors? Okay, maybe you'll use row reduction to solve it. Okay, but now what we're gonna use is this method here, orthogonal basis method. Because notice that this U1, U2, U3 is see before, correct or not? Just now, okay, from the previous example, we know that U1, U2, U3 form a orthogonal set, or they are orthogonal to each other, or orthogonal, or orthogonal, okay, with each other. And then the theorem tells us that, from the theorem, they are linearly independent. But you see, you have three linearly independent vector in R3. Meaning what? By spanning set theorem, no. By another theorem, by the basis theorem, they form a basis for R3. In particular, they are the orthogonal basis. Okay, in particular, they are orthogonal basis. So you can use the previous theorem there. Okay, so from the theorem, from previous theorem, we will write y in terms of C1 U1 plus C2 U2 plus C3 U3. How to get this Ci? Where Ci equal to what? You take your y dot with your basis vector and then divided by the length square. So you divide by ui dot ui. Okay. Can you try and compute the Ci? Try and compute Ci. Okay. I give you 3 minutes. Try and compute Ci. Okay, try and compute this, and then we will try and verify, and then we see the magic, and then I show you why the magic works. So there are 3 of them you need to compute, C1, C2, and C3. C2 and C3. So you just basically computation is not hard, just write down all your vector. Get the horizontal. Okay, so we got C1, C2. C1, C2, and C3. So you just line up your vector. Okay. So you should get 1, -2, and -2. Right. I'm getting this number. What do you get? Huh? What do you get? Very complicated sound. Huh? Seriously? 前2个对. What do you get for the third one? Huh? What do you get? -1? 132除以155. Okay. Let me write down what's the calculation you did here. Should be -33 over 33 over 2. Really? Okay, let's write down one more step here. Should be -3 minus 2 minus 28 over 1 over 4 plus 4 plus 49 over 4. Hey, by the way, last time we start with a determinant calculation, right? I already put that in my lecture notes. Both way I provided. One way you do cofactor expansion, the other way you do row operation. Actually, the row operation one turns out to be longer. Okay, so it's not recommended. Okay, anyone got this? Everyone? You get stuck? Okay, okay. So, sanity check, right? So let's do the check. So we should write y equals to u1 minus 2u minus 2u3. Okay, so what's our y again? 6, 1, 6, 1 minus 8. And then u is u3, 1. And minus 2 u2, -1, 2, 1. Okay. Okay, here I got a -2. Okay, can you check that actually this is true? Quickly do by inspection. Okay, maybe just do the first one with you, others you do yourself. So here -2 minus half, you get 1. So here you get 2, 1, 2, 3. So you add up to 6. Okay, then you check the rest. So you might think that, hey, the solution only 1, -2, -2. We compute so many dot product here. Seems like more complicated, huh? Okay, but you need to understand. Maybe if you ask the computer to do row reduction, it is much complicated than you ask the computer to do the dot product. Right? Dot product, you just tell the computer one step, and then the computer just put in different factor. But if you ask the computer to do row reduction, right, it will change, right, based on what you have at each step. I don't know. Okay, so it depends. Okay, which one is faster? But why it works? Why it works? What do you think? Why it works? So let me write down the theorem again. Let's talk about why it works. So let's say u1 dot u2 u1 u2 dot un b and orthogonal basis. Then y is c1 u1 plus c2 dot plus un cn. Right? Ci is equals to y dot u over. Actually, this formula here suggests you what you should do. It starts with what? Y dot with a u. Okay, so u here is ui, not u1. Okay, so what do you do here? So if you have this expression, right? Okay, first of all, because this u1 to un is a basis. So meaning what? Surely you know there exists these coefficient here. The problem now here is how to find this coefficient. Huh? And then my hint here is this is hinted by your formula here. Okay, this is hinted by a formula here. Okay, so let's say we put a proof here. What can you do? There's one term you never see before, right? Y dot u. I go try and try it. What happens if you dot y dot u 1 here? Meaning what? You are dotting your linear combination with this u1. Correct or not? Okay. But if you dot with this u1, what happens? The dot product is distributive. Okay, so you can dot every terms inside the sum with u1 also. But what happens now if we do this? You notice? What happened? We are dotting u1 with different ui. What happened? They are all 0. Because this is an orthogonal set of 0. Only one guy will survive, which is C1. Okay, if you dot with ui, then the u item will survive. Then how do you find C1 here? This implies that C1 equals to u dot u1 over u1 dot u1. Okay, yeah. Right, so you do it for any I. It's the same. Okay. Can absorb one more concept before quiz. One more, then we will have a break. Okay, one more concept. I want to teach you first, then next week maybe we can repeat because it's quite an important concept. So I want to plant in your head first. And next week we're gonna say it again. Okay, so let's talk about one more concept and then we will break for quiz. Okay. So let's talk one more concept here. Right. So here the concept is called orthogonal projection. Orthogonal projection. Okay, so just now I gave you an idea, right? If they are linearly independent, either they are 90 degrees of each other or either they are not. Okay, so we're gonna talk about this general situation here. So let's start with two vector, even y and u in Rn. Okay, so because I cannot draw a random Rn for you, I just draw two-dimensional case. So let's say we got a y here, and then we got a u. Maybe they are not same length. That's fine. Okay. So what we're gonna do here is we wish to write, let's say, y equals to two parts here. Okay, equals to two parts. That is y hat plus another vector z. Okay, both of these don't know what is it. So let me tell you what is it. Y hat should be a scalar multiple of u, and z is the orthogonal guy to u. So what do I mean by this? Okay, this is very, how to say, very diagrammatic. Okay, so because just now we always split a vector into x component and y component, right? If you learned physics before, we split a vector into x component and y component. But now we're gonna split y into a u component and a component orthogonal to u. So you can think of it like I extend this u a bit, either extend or become shorter, doesn't matter. And then I fill out this orthogonal part. Okay, so this orthogonal part is going to what we call a z. And then this extended or scaled u is what we call the y hat in our case. Okay, no? So we give a random two vectors, we can fill it out, become a right angle triangle again. Okay, so this is what we're gonna do. And then we will introduce a lot of naming, just name, so don't worry. But the idea is this. So I give you a vector, we fill it up into a right angle triangle. Okay, so how to do this? How to find it? So let's see how we find it. How long we need? Okay, so first question is how long we need. Once we got this, we should get z already, because z is equals to y minus this alpha u. Okay, so the problem is how long we need. How long do we need? Okay, so let's see how we figure out how long we need. So this means what? This means that, okay, so let's derive it. So one property you know that is we want this z dotting with u should be 0. Okay, because we want to fill it to a right angle triangle, right? Okay, we want these two things to be 90 degrees. And then z by our definition is y hat, y minus y hat. Okay, the one that we extended in the u direction. But we're going to find what is alpha, right? So let's put our alpha back into here. Okay, so meaning the length that we're going to introduce, right, should satisfy this equation. So we try to solve for alpha. So let's solve for alpha here. Well, dot product is distributive, so we can dot u with every term inside here. And we obtain a relation between alpha and my vector. So can you see something here? You see something here? Okay, alpha actually is equals to the y dot u over u dot u. Similar to the form that we see just now, right? Every scalar is coming from where? You take your vector dot with your basis and then divided by the length of your basis, the square of the length of your basis. But if we try to expand this, it is even more interesting. So because we have u on both sides, right? So, well, we apply the dot product formula that relates their length and their angle, okay, divided by the length square. So in principle, what do you have? How do you get this scaling? Actually, you need to compute the length of your y first, and then divided by the length of your u times the cos of their angle. Okay, and then this is what we define as a y hat. The scale u is the orthogonal projection. Orthogonal projection of y. Yeah, orthogonal projection of y onto the line. Okay, the u, the span of u in particular. Okay, which sometimes we don't put y hat. We will put as a project. Project to where? Project to this line here. Project y onto this line. Okay, or we will write it as y hat equals to the projection of y And then what's that? It is just y dot u over u dot u. Okay, so meaning what? If you look at this picture again, we are trying to project this L down to this u direction here. How to project? You need to form this right angle triangle. Okay, so this is an orthogonal projection because you are using this z to project it. Okay, so in other words, what? In other words, says what? If you look at this formula closely, you are doing P projection here. Yeah, P projection. You see, this term is the same term. You are doing P projection. So if you have bases, right, you are projecting to different bases. And this is the picture we do just now, right? Just now I show you the n-dimensional Pythagoras theorem. You do the triangle, you do triangle, do two triangle here. So you project down and then project. Then you project from a 3D space to a 2D space, and then you project to x-axis. And you also can project to y-axis. Orthogonal projection. Okay? Okay. Any question? No question? No? Okay, if no question, I think we will come back to orthogonal projection again. So let's break until 11:25 and then prepare for the quiz. Here, Miga.
这个有，就是
是，好的，
这个，这个，但这个和这个有关系。
你说这个题目在说什么？
对，
他说，如果你有这三个东西的话，他叫你检查，说 v1减掉3乘 v2加5乘 v3会等于0。你 try 过了吗？你 try 了 ，OK。然后现在他叫你用这个 information to find a basis，OK。所以这一个条件告诉你了，他们是 linearly dependent，OK。一个是 dependent on 其他两个。对，OK，所以 spanning set theorem 告诉你什么？如果 dependent 的 vector 就把它丢掉，所以你就丢了，你丢哪一个都行，其实你丢起，因为你可以，比如说你 V1可以写成另外两个的 linear combination，当然也表示 V2也可以写成另外两个，所以现在问题是我的答案就是说，我有三个可能性，OK，可以选这个，可以选这个，可以选这个。然后 turns out 的这三个可能性都可以，因为他们已经不是 linearly dependent。
这个答案说是零不在，但是如果
OK，我知道你讲的，但是我们现在不是在 evaluate t，我们不会 evaluate t 的，我们是把 t 看成一个就是看成它自己，就是 t 就是一个不是零的东西。
T
因为 a 等于零跟 t 等于零的概念不一样，现在，因为 a 等于可以选零，是因为 a 是可以有选择，但 t 还没有让你选择，我们没有在 evaluate 它
T 是
，t 就是一个 t。
T 方
当你 substitute t 等于某个号码的时候，对不对？但是在这个世界里面 t 就是 t 是零的，so that's why 你看到我们上课我们会经常说，你让我写，我们会经常说，t 和 t square 没有关系，只是你要想一下为什么它没有关系。如果像你讲的，哎，这样我不是可以想100吗？这样不是有点糟糕？所以其实它就是他自己一点。
先小飞这个问题啊，
哎，
如果我没有点这边呢，有一个方面要这样子呢。如果我在这边开始写会怪嘛？会这样吗？因为我怕了。哦，没事。
有这样写过的？
哦，那对。
好像课本这样子写，是不是？等一下，
不会写话，
从这边开始写。
直接做。
哦，
哦。但是我写的话也会怎么样？
不会，肯定是写的更好啊，把就是说来这边就，那你的
要紧张。
都考过2次啊，
我要修我字。
刚才好像有一个味道飘上来，我讲是不是他？
所有的颜色。
没有，我想要文书。书香啊！你宿舍的味道？哦，这是味道。Try make your chair into the same row so that later easier to distribute. Oh my gosh. Okay, one answer. Calculator. No need calculator. You don't need calculator. It won't be hard today. That's fine. You'll be good. That's Nian Yo here. Nian Yo. That seems like quite a few dogs here. Be dangerous. Yeah, before you start, try not to discuss your solution. Yeah, try not to discuss your solution.
Okay. Yeah, actually, solution is not the most important part. The most important part is the step. Okay, if you know how to apply formula, your logic correct or not. Okay, should we start soon? Okay, if everyone ready, you can put back your. Yeah.
Ready.
You ready? Wow, so early. Wait, before, wait, let them. Okay, you can stand here first if you're ready. You can stand here first. Let them keep their electronic devices first. Okay, you can keep your notes, electronic devices. You can bring your calculator. Yeah, put all your notes away. Okay, everyone that sitting on the aisles now, you can come and get for your roommate. Sorry, you got time up slowly. Once you get it, you can just start. And then there's one typo I want you to make here. The two here become a minus two. Okay, the red one not clear, is it that blue? That's blue. Okay, so the reason is two questions per connection. Okay, so please set your time for calculation. Okay, please make this adjustment. Don't start calculate yet. You will calculate the wrong matrix later. Please make this adjustment here. Become a minus two. Hey, keep your notes, keep your notes, keep your notes. Keep your notes. Please make the correction first before you start. You got plenty of time. And please make this correction. Don't start compute yet. Later you compute. Not enough. Not enough. Sure. Hey, here they got extra. And here also got extra. You need how many more? Two more. How many more you have?
Four.
Much more? 20? Let's see. How much. Like 2%. Don't need to rush. I got enough time. Okay. Make this correction. 2 become minus 2. Hello. So there are two pages, right? There are two questions only. So question one you can answer to the other page. Question two you also can answer to the other page. Because I know that maybe Kramer's rule need a lot of space. So you can write on the whole page. Okay. First question on the whole page. And second question also on the whole page. question 1 must use Cramer's rule, because last time we used the elementary one matrix, right? So this we will test on Cramer's rule. Cramer's rule refers to the adjoint matrix. You need extension or not? Yes, sir. Okay, 5 minutes. For those who already done, please check your solution. Please check. And then check your name, check your ID, correct? Okay, 1 minute left. So take your answer, clean out your answer, write down your name, student ID. Okay, pass to the person in the aisle. The person in the aisle, please help me calculate. Don't just collect. Please help me calculate the right number. Make sure you collect every person in your row. And then each student, make sure you hand it. And then open it up. The name page face up. Open it. The name page face up. Yeah. If you have hand in, you can leave. Make sure you hand in yours. I mean, open up. Open up. If you have anything, please you can leave. Hey, collect. We already have extra time already, so please collect. Line. Quick. Great. Make sure you hand in before you leave. Okay, thank you. Wait, okay, thank you. Quick. How many rows? 2 more rows. 3 more rows. Quick. Yeah. What's the last question? What happened? No idea what to Why? Just confirming country, yeah. Express in top linear combination. No idea. Okay. Let's see. Okay, bye. Bye. Hey, how many row? One more row. 快点 Amber 催他。快。
然的路啊，是那个涂掉一行那个肉，然后换去别的去找那个行的。他们是 enjoy 什么路？你不讲就完蛋了，想半天。
怎么？会断？
是没有爱的。
哎，看我乱了。其实
来，我来吃饭。
来炒菜。
还喝咖啡是吧？
对，别管。
小错，今天搞这对呀。 看我的过程，我都能看懂。你要看我打楼在
12，
你看我大我不看不懂。
我可以看哪一个？
看不懂我的过程。
我觉得这题其实是很短的。啊？
不错啊，
我不知道。
你看那里面都有它。哪一个比较？
哦，我没有讲我哪一题错。
叫我。
不懂我的解法，就放进来罢了。
然后再放 inverse。
62场，
说没？
62，啊，12，
对啊。
对啊，6场。对啊，我自己加，你不要讲先，我讲，给你帮一下。你几张？62，是吧？28啊，对，对啊，两个人的，对，不懂，看下他们是生病还是做梦。这个这样做哎，其实第二个很简单哦，第二个不是3堂吧？第一个啊，第一个你第一个算没有，第一个你第一个都算了 invertible 吗？那肯定是你连那个 span 了。
我后面发现本来想录这个，后面
用 no reduce 啊，你这边都 determine 不等于。
后面我就说，后面我就直接得出来，可以吗？
连这个的话，其实直接就是涨价的，不是？这是它来的。
然后再
哎，不是，我想一下，是它的 inverse 还是
它的 inverse 乘以
它的 inverse？
乘以这个，这个乘以这个，这个乘以这个，这个乘以这个，
哎呦，
这个 inverse 乘以它这个相对，
然后这个是这样做，
就可以算出这
对啊，
个，
对啊，对啊，对啊，
这个。
不错啊。它是在写的，不是，我98张了
88。
，88张，28张。这个要这样做，1010啊。你可以这样做，其实我放11可以吗？
对
但是问题是你算出来的东西不是就是前面算的东西？
好像就是前面
答案是对的，这是答案是对的。对啊，对啊，对啊，对啊，对啊，
因为
对啊，
反正就是有一个，
应该
我要考虑选择题啊，我不掉，然后我自己又不掉，因为我们发现就是 inverse，然后后面就直接写出这
对
个，
啊
就是
，sorry，肯定还有这什么啊？
好记。
错。